This is a lesson on the basics of circular motion in the kinematics unit. While I've left a more detailed account of angles for the unit circle lesson, I want to remind us of two important concepts about angles that we'll need as we move forward. The first is the conversion factor between revolutions and radians, which we will be using throughout this lesson. Also, we will be moving forward towards angular vectors, which inherently necessitate the assigning of a coordinate system so that we know which direction is a positive motion and which direction is a negative motion in circular motion when something is moving clockwise or counterclockwise. And I will show this as we move along. Another quick skill that I wanted to put in place as we move forward into representing more complex systems is representing direction in 3 dimensions. Up, down, and left and right are pretty well easy to do because they are in the plane of the presenting medium. You can see up, right, left, and down. In and out then require different symbolization in order to construct a 3-dimensional situation. And we do this with the use of an X and a dot, respectively. The way to remember is to think about an arrow. And when I draw an arrow, I think about the head of the arrow and the fletching at the end of the arrow that makes it fly straight. If the arrow is moving away from me, I will see the end of the arrow and the fletching and therefore represent it with an X. That's moving away, which we call into the page. As opposed to when the arrow is coming towards me, I see the head of the arrow, which looks like a dot, and we call that out of the page. So now we can represent the 3 dimensions of a coordinate system with symbols. Sometimes when we look at 3D sketches, we can provide a 3D sense of the object, which you can see on the right-hand box here. But if I looked at this box directly from the side, and I may represent this with like a side view, or even from the top, if I look at it from the top, I cannot tell that there is an extended object. I just see that surface. As we move forward in circular motion, we will anchor with the idea of an angular displacement resulting from the movement from an initial angle to a final angle. And as you can see in my picture, I can designate an initial angle and a final angle, the angular positions. And when an object moves through that angle, we say it experiences an angular displacement. This angular displacement corresponds to an arc length. For an object on the outer rim of the circle, it traverses a portion of the circumference, and it's related to the angular displacement by a factor of r. And we will continue this relationship as we move forward in that an angular measure corresponds to a linear measure at a given radius. In similar logic to linear velocity, now that we've defined angular displacement, we can define angular velocity, which is the time rate of change of angular displacement. How many angles was traversed through in a certain amount of time. I'm going to note that this representing symbol is the Greek lowercase omega, which represents angular velocity. Some people like to write W, but it really has rounded edges on the bottom, so make sure you're doing that in your own work. The SI units is radians per second, not degrees per second, radians per second. And we will keep that in mind as we do dimensional analysis in further equations. Angular velocity is a vector, and you can see that what I have drawn here in this picture. I have a disk spinning about the central axis. This is a side view, a straight-on side view, and this is sort of a perspective view so we can see that it's 3D. You can see that the top of the disk is coming out at you and the bottom of the disk is going into the page. And the way we figure out the direction of the angular velocity vector is with right-hand rule 2, which I like to call the curly right-hand rule. It's very intuitive. The top of the disk is coming out at you and the bottom of the disk is going into the page. So if I do that, you can see how if it's coming out at you and going into the page, I'm going to get the omega pointing to the right here. Okay, and that's right-hand rule. It's very intuitive. You curl the angles in the direction of the turning motion. The vector is then your thumb. An important quality to note about angular velocity is that all of the points on the object experience the same angular velocity. Any point along a radius, as it traverses an angular displacement, all of the points will traverse the same angular displacement. And they will all do this in the same time period. And what we see is that the angular velocity for each one of these points is the same for point 1, for point 2, and point 3. Similarly, in following the logic from angular velocity, if we have a change in angular velocity, we can designate angular acceleration. And the equation is down here, change in angular velocity over change in time. This is represented by a Greek lowercase alpha, which is drawn very simply. The SI units on this is radians per second squared. Again, we can use right-hand rule in order to figure out an angular acceleration vector. In whatever direction it is speeding up or slowing down, we will point our fingers in that direction, and that will give the direction of that vector. Similarly to angular velocity, all points on an object experience the same angular acceleration. All of the points along a radius, 1, 2, 3, have the same omega initial for all of them. And they all move through the same angle in the same amount of time, so therefore they will have the same omega final. Therefore, all of their alphas are equal to each other. Alpha 1 equals alpha 2 equals alpha 3. All of the quantities that I introduced to you just now are angular. We can convert from angular to linear tangential quantities by a simple factor of r, and we saw that with angular displacement. To get from angular displacement to linear displacement, we just needed a factor of r, and this is the arc length. And this is a linear displacement. When I think about angular velocity and linear or tangential velocity, if this thing is moving in a circle, each point along the outside of that circle has a linear velocity, and it will be tangential to the circle. Sometimes we will call this v tangential. I can relate it to the omega by a factor of r. Very similarly, if this object is accelerating, I can find a tangential acceleration by multiplying a factor of r as well. Let's work on an example problem that covers these concepts. And I've put up here the equations for us to have very conveniently. This is the truck wheels problem, and I put a wheel over in the corner for us to draw on. It says a truck with 32-inch diameter wheels is traveling at 60 miles per hour. So I'm going to assume this wheel is rotating at a constant speed. It just says 60 miles per hour. And this is a linear or tangential speed, not an angular speed. When I think about the wheel in the reference frame of the truck, the wheel's turning so that every point on the wheel is moving at 60 miles per hour on the outer rim. So I'm going to draw that on here, v tangential, and that's a 60 miles per hour. I know these two quantities are related. It says A, find the wheel's angular speed in RPM. So I want to find angular speed. I know a linear speed, and they tell us the diameter. I can find the radius. Radius is 1/2 the diameter, so a half of 32 is going to be 16 inches. I can relate the tangential velocity to the angular velocity with the equation omega r. We want to find omega. I will solve for omega with a little bit of algebra here. I get the tangential velocity over the radius. And I'm going to put up here 60 miles per hour over the radius, which is 16 inches. I have to deal with some units here, but I'm on my way. Let's convert from miles to inches. 1 mile equals, here's the conversion factor for the number of inches in a mile, 63,360 inches, or in 1 mile. I'm also going to notice that the question asks for revolutions per minute, and I'm going to notice this is in hours and go ahead and convert it to minutes. So in 1 hour, there's 60 minutes. As I look at this calculation, I notice there's a 60 here and a 60 here. I'm going to work out some dimensional analysis too. I'm going to cancel some inches. Those cancel out. I know my hours cancel and I know my miles cancel, and I'm left with a per minute up here, right? 1 over minutes. So when I calculate this, I can simplify real quick to 63,360 over 16. And the units become radians per minute. This may seem weird because you're asking, where did the radians come from? But what happens is when you cancel a linear distance over a linear distance, we can have radians left over. And in this way, radians are dimensionless. And I've left this for another lesson. What we can note is that this is in radians per minute. When I put it through the calculator, I get 3,960 radians per minute. I need to do one more conversion to revolutions per minute. In 1 revolution, there is 2 pi radians. The radians cancel. I can see that I have revolutions over minutes left. I divide that number by 2 pi, and I get a value of 630 RPMs. In 1 minute, that wheel will turn 630 times at 60 miles per hour. Pretty interesting. The second part asks, how fast is a point on the wheel 10 inches from the center moving in miles per hour? Well, I know all of the points on the wheel, no matter where they are traveling at that same omega. So if I have point 1 on the outside and point 2 on the inside, I know that omega 1 has to equal omega 2. I'm going to carry the equation down I have from up here. I know that omega equals V over R, and kind of put that into that equation. V1 over R1 has to equal V2 over R2. And I'm trying to solve for V2. What is the second velocity? You could use 630 and go through that calculation, and that's perfectly fine, but this is going to leave us a nice ratio. So if I solve for V2 in this equation, I multiply by R2 on both sides, I get V1 R2 over R1. This becomes 60 miles per hour. The first dot is going 60 miles per hour. R2 is 10, and R1 is 16. Plug those numbers in. You get 600 over 16. Notice that this is a miles per hour, and over here I get inches over inches. And when I do dimensional analysis on this, I'm left with miles per hour. When you run this through your calculator, you get 37.5 miles per hour. And that makes sense. For a point that is closer into the center, it will move slower in order to go through the same angle. The last part here asks, how many revolutions does a wheel go through in 10 miles? When I think about revolutions, I think of about an angular displacement. And I know the equation for angular displacement would be delta S over R, right? Delta S is delta theta times R. I solve for delta theta and I get this equation. To adapt it to this problem, I have 10 miles, okay, 10 miles. And I'm going to note that I'm going to have to convert this to inches. 1 mile is 63,360 inches. And if I divide by the radius, that's 16 inches. All of my units cancel. The miles cancel, the inches cancel. And remember, when all of the dimensions cancel, we get radians. It's a dimensionless quantity. It's a dimensionless unit. I know it's weird to think about, but that's what it is. When I multiply and divide all this out and run this through my calculator, I get 39,600 radians, which we kind of knew, right? It should go 10 miles in 1 minute, and it's going 3960 radians per minute. So I'll go drive 10 minutes and get 39,600 radians. I still need to convert this to revolutions per minute. It wants revolutions. Let's convert this to revolutions. Not revolutions per minute, to revolutions. There's 2 pi radians in 1 revolution, and you can see that the units cancel correctly here. I take this and divide by 2 pi, and I get the number of revolutions, and we get 6,303. I'm going to round it to 6,300 revolutions.